Okay, and then finally, there are these networks that are less well understood. Here you see a kind of electrician's diagram with the output being fed into the input, and these Hopfield type neural networks, they're studied by a different community, so by people working in statistical physics and looking at dynamical systems and attractors and strange attractors and that sort of thing. And people have used these for building associative memory. So you can put in some data, and then the system, by reinforcement, brings up the concept that it had once learned in this fashion. They may be useful, but it's very difficult to understand mathematically what is going on in these networks. So while the feed-forward networks that I've shown you before, while they have been understood and embraced by the statistics community, this is well, a different field and hard to draw general conclusions as to their functioning or failure of functioning. All right. So we're left with this design choice. How many hidden units, how many layers in the network do we want, etc. Broadly speaking, this is called the problem of model selection. And empirically, the following picture emerges. So for a given training and test set, every method has a risk or an error. And most methods allow you to either implicitly or explicitly adjust the flexibility. So for example, LDA would be stiffer or would be less flexible than QDA, or a neural network with few hidden neurons would be less flexible than one with many hidden neurons, and so on. And if you now plot the empirical error or the training error, so that's the error on your training set, as a function of your model flexibility, you typically find that the more flexible your model, the better your fit to your training data. Okay, so if we think about nearest neighbor, then one nearest neighbor would be the ultimate example where you have zero training error, but you may have some test error. And if you take the 101 nearest neighbors, your method might become too stiff. So you might not fit your training data well. And then there is the prediction or test error. So the performance of your method on an independent test set. And again, taking one nearest neighbor as an example, one nearest neighbor in fact would have zero error on the training set, but a notable error on the test set. And the difference between these is called the optimism or false optimism. So in the domain of great flexibility, we will overfit the data. If we take very stiff methods, we may underfit the data. We may have too much bias in our method. We may not be able to render all the intricacies of a decision boundary, for example. So this is why the training error goes up if the method becomes too stiff. And we're, of course, interested in finding the optimum. And rather than finding the global optimum in case of doubt, people will prefer methods that are a little bit simpler. So you're either looking really for the optimum, or you're looking for a method that has fewer parameters but is still close to the optimum. And then you would say, okay, this is the optimum flexibility for your method. So to give you an example here. I have drawn a couple of training sets from an underlying distribution that you know very well. The green line again would be the base decision boundary, the best possible classifier, and I have fitted to each of these training sets a quadratic discriminant analysis classifier, and the resulting ellipses are shown here. And well, we see that there is some variance. So as I go from one training set to the next, I get slightly different results, but these are always quadrics, of course. The variance here, it exists, but it's relatively small. But on the other hand, I have some bias. So the ideal classifier, the base classifier, for instance, has this small annex, and it has this extra bump here. And well, QDA can only produce quadrics. So no matter how much data you put into your QDA classifier, you will only get out an ellipsis or a hyperbola or a parabola. So we have a little bit of variance, but we have significant bias. So bias is the difference between the average of what your method will deliver across many training sets and the ideal classifier or the ideal method. And then on the other hand, you see the decision boundaries for the 1 nearest neighbor classifier treated on many training sets, and on average, this will have zero bias. So on average, this would give me just the right decision boundary, but you see as I go from one training set to the next, I get very different results. So the variance is large. Now, if you are lucky enough to have lots of data, then you would partition your data set as follows. You would take the bulk of your data for training, and then some part for validation, and then reserve an independent test set. And while you tweak the parameters in your method, and while you still think about if you want to use neural network or support vector machine or the QDA, so while you play with your method, you only ever look at the results on your validation data set. And the test data is really reserved for the final test. So once you've committed yourself to using this classifier with those parameters and so on, then you can apply to the test data just once to see how well you have done. Now, in real life, typically data, there's too little annotated data, or in general too little data, and then people resort to resampling strategies. I would say nowadays people resort to resampling strategies. In the older days, people tried to estimate this optimism by using criteria such as the Acker-Icke information criterion, or the Bayesian information criterion, or the network information criterion, or minimum description length. So all of these are methods that try to estimate the degrees of freedom of your method and that penalize the quality of fit with the number of parameters. Because the more parameters you invest, the better your fit. However, all of these assumptions, all of these methods have some underlying assumptions. All of these measures have some assumptions that may not be fulfilled by your training data, or that may not be fulfilled by the method that you're looking at. And nowadays that computational power is abundant, people instead resort to these resampling methods. And in particular, I'm going to mention a few. There's the jackknife and the bootstrap, and there's a 0.632 estimator, all of which I'm not going to discuss in detail, and there is cross-validation. And empirical studies have shown that cross-validation amongst all of those is the one that gives you the best estimate of this optimism, or that gives you the best estimate of what flexibility your method should really have. So in cross-validation, you partition your data into k folds, and then you train on k minus 1. You predict on the kth, and well, you know, collect your statistics. So you can then count how often did you do, did you get the correct solution, how often did you get the wrong solution, and then you go to this step. And it's important to go to this step and not straight to that step. Going to this step will assure you that all of these test sets, that all of your k test sets are non-overlapping. Whereas if you keep going back to the first step, you get a different method, which is called repeated holdout, and there you can have overlapping test sets. By the way, this partitioning into k folds, this can be stratified. So, for instance, if you have very few examples of class number 2, you may want to make sure that you have some examples of class 2 in each of your k folds. And by the way, you can, if you have lots of computational power, you can even repeat this whole process. So you can do repeated cross-validation, meaning repeated departitioning, and so you can, by repeating all of this all together, this would be repeated cross-validation, and this will give you even better statistics. So one of the benefits is that you get not just one, but you get k curves. So you will get, for each flexibility of your method that you adjust, you will get not just one precision, but you will get a total of k errors out. And doing that for every possible parameter setting in your method will give you both the average accuracy and also the spread around this mean. Remains the question of how to choose k. We can look at two extreme cases. We can take k very small. This will, in the extreme case, k equals 1, or leave 1 out. Cross-validation. K equals 1 is not perfect for the following reason. Let's say we have sampled a training set T1 from our source. This is now an abstract space of training sets. If we now start omitting single observations, this means that we can only move around small distances in this space of all training sets, because we're just leaving one sample out. So it means we're almost not changing the training set. So we only admit for minor perturbations. but from the same data source, we might have obtained a training set T2 with equally small perturbations. And by showing these two training sets, which I assume you can get from your source, and by showing these very minor excursions that you can achieve by using leave one out cross-validation, I'm trying to qualitatively indicate that these perturbations will be too small. So overall, as you estimate let's say, the mean performance of your method, you will get a very different answer depending on whether you work with training set 1 or training set 2. So you will get high variance. On the other hand, if you now, this is not k small, this is k large. So, excuse me. If we set k equals to n, so if we set the number of folds, the number of samples, it is then that we can call this a leave one out cross-validation. And this is what I've just been trying to say. The other extreme would be to say that we have, for example, k equals 2, we have 2 folds, and then we have large perturbations of our training set. So we would perturb our training set very much. It means we would well cover the space of all training sets. So this is the k equals 2 case, the yellow case. We would perturb our training set very much, but we also discard half of our data. We only use half of the data for training. And given that most methods have a learning curve, so the more training data you put in, the better your results should be. Throwing away half your data can mean that you're doing too badly, or you have less training data, or you pretend having less training data than you really do, and you can hence have an estimate of your error which is overly pessimistic, or you can get a biased estimate. So k should be somewhere between 2 and n, and again, people have studied this empirically, and the recommendation is to use 10 folds. And by the way, so after you have decided how you want to parameterize your method, you would use both the training and validation before applying it to the test set. The test set will then give you your best estimate of the performance, but then before you really deliver your algorithm, before you roll it out to the real world, you would use all the data that you have. But then, of course, but you can only deliver the precision estimate that you had to obtain from the test set, so from training on these two. Okay, and so cross-validation, if you can afford it computationally, this is really the thing that you should be doing. So not use these theoretical estimates, not use these resampling methods either, but really just do cross-validation. Any questions? N is the number of samples. Yeah.
So how can this algorithm
because you train on k minus 1 folds, so you train on the entire data training set except for one, and on this single one you're going to make a prediction. And if you do that, then well, you're guaranteed not to have a stratified folds, yeah? Because you just have a single sample in each of your folds.
And should be better to get any loops. Should be better
The question is, does it get better with more loops? No. So you will get out k numbers, and these k numbers will have a spread. And if you repeat this entire procedure, you will get another k numbers, which will give you an even better estimate of your distribution. So the error will not improve as you repeat the cross-validation, but your estimate of the distribution will improve as you repeat the cross-validation procedure. Any more questions? Okay, so I think we've covered a lot of ground today. We've looked at starting with the perceptron. We've looked at artificial neural networks and in which sense they constitute a mapping to higher dimensional space. And by means of the function counting theorem, we have seen why the rationale, why would you want to map to higher dimensional space. We have also seen the difficulties in fitting this, the parameters in a neural network well. And you will have a chance to further explore these difficulties in your exercise. And we finally looked at cross-validation as an objective means of fitting all those three parameters in your method. So in neural networks, you could, having a big enough computer, you could do a grid search across all the possible numbers of neurons in your hidden layers, and grid search across different settings for your activation function and so on. And it would really be the cross-validation that tells you statistically what setting of all these parameters seems to be optimal. I have alluded a lot to support vector machines, and this is what we're finally going to look at next week.